Hey everyone, here are some of the notes on 10.2. So now we're looking at means, and so it's very similar to when we looked at means with one mean, but now we're comparing two means. So remember that your mu is your mean, so when you see mean, you think mu. Alright, so suppose we want to compare the mean of individuals with a certain characteristic in population 1 and population 2. So if you want to look at the average number of men versus the average number of women, or the average number of senior citizens versus the average number of people in their 40s, or whatever you want to do, that think about a certain thing. So average effectiveness of treatment 1, treatment 2. So remember that your parameter is to do with the population, and that's what we're dealing with our mu's. So mu sub 1, mu sub 2. Our statistic, this is our x bar. X bar sub 1, x bar sub 2. And your sample size is still going to be n sub 1, n sub 2. Alright, so we can compare the populations or treatments by doing inference about the difference again. Okay, so this is where we're looking to compare the two, so we are subtracting the two differences, or the two mu's, so that we find the difference. Okay, so we have a sampling distribution of x bar sub 1 minus x bar sub 2, so we have two sample means. Okay, so we choose a simple random sample of size n minus 1 from population 1 with mean mu sub 1 and a standard deviation of sigma sub 1, and an independent simple random sample of size n sub 2 from population 2 with a mean mu sub 2 and a standard deviation of sigma sub 2. So the shape, if the population is normal, then the sampling distribution is normal. In other cases, we have to make sure that the sample sizes are large enough. So we're going to use the central limit theorem so that it's approximately normal. Which means that our sample sizes need to be greater than or equal to 30. So n sub 1 greater than or equal to 30, n sub 2 greater than or equal to 30. Okay, our center is just like when we did our sampling distributions. Okay, when we subtract the two, we just subtract their means. Alright, and then this, look very carefully, this is the variance. Okay, so it's just like when we did our sampling distributions and we had to square our standard deviation of each. We have to do that. So if you're wondering why, you still need to check the 10% condition. Alright, so let's look at an example. Medium or large drink. A fast food restaurant uses an automated filling machine to pour soft drinks. The machine has different settings for small, medium, and large drinks. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed from the machine follows a normal distribution, with mean 27 and standard deviation of 0.8. When the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution. So they both establish normal, just for you to note, with a mean 17 ounces and a standard deviation of 0.5. To test the manufacturer's claims, the restaurant manager measures the amount of liquid in each of the 20 cups filled with the large setting and 25 cups filled with the medium setting. So we have independent trials where we get our samples from, so the shape is going to be normal because it both comes from normal distributions. So we're looking at x bar sub 1 minus x bar sub 2. Or if you wanted to make it large and medium, that would also work. If you want to do x bar sub L minus x bar sub medium, it will be normal because sampling comes from normal population. Now your mean, if you want to do x bar sub 1 minus x bar sub 2, it might help if we put 1 is going to be large, 2 is going to be medium, or if you wanted to use the L and N, if that suggests there, you can. But it's just going to be mu sub 1 minus mu sub 2, which is just going to be 27 minus 17. So we should see an average difference of 10 ounces. Alright, and then to find our standard deviation, we're going to have to square both to find the variance. So the 0.8 that we had divided by our sample size plus the 0.5 we had squared divided by that sample size. And you type that in your calculator, you see it's 0.205 ounces. We don't need to check the 10% condition because we are sampling without replacement. So if there was replacement, but it's a machine, so we don't have replacement. So that's going to be the first part of your notes.